In probability theory, the normal or Gaussian or Gauss or Laplace-Gauss distribution is a very common continuous probability distribution. Normal distributions are important in statistics and are often used in the natural and social sciences to represent real-valued random variables whose distributions are not known. A random variable with a Gaussian distribution is said to be normally distributed and is called a normal deviate. The normal distribution is useful because of the central limit theorem. In its most general form, under some conditions which include finite variance, it states that averages of samples of observations of random variables independently drawn from the same distribution converge in distribution to the normal, that is, they become normally distributed when the number of observations is sufficiently large. Physical quantities that are expected to be the sum of many independent processes such as measurement errors often have distributions that are nearly normal. Moreover, many results and methods such as propagation of uncertainty and least squares parameter fitting can be derived analytically in explicit form when the relevant variables are normally distributed. The normal distribution is sometimes informally called the bell curve. However, many other distributions are bell-shaped such as the Cauchy, Student's T, and logistic distributions. The probability density of the normal distribution is f x mu sigma 2 equals 1 2 pi sigma 2 e minus x minus mu 2 sigma 2 display style f x mid mu sigma caret 2 equals frac 1 sqrt 2 pi sigma caret 2 e caret frac x mu caret 2 sigma caret 2, where mu display style mu is the mean or expectation of the distribution and also its median and mode. Sigma display style sigma is the standard deviation. Sigma 2 display style sigma caret 2 is the variance. Topic definition. Topic standard normal distribution. The simplest case of a normal distribution is known as the standard normal distribution. This is a special case when mu equals 0 display style mu equals 0 and sigma equals 1 display style sigma equals 1, and it is described by this probability density function phi x equals 1 2 pi e minus 1 2 x 2 display style var phi x equals frac 1 sqrt 2 pi e caret frac 1 2 x caret 2. The factor 1 2 pi display style 1 sqrt 2 pi in this expression ensures that the total area under the curve phi x display style var phi x is equal to 1. The factor 1 2 display style 1/2 in the exponent ensures that the distribution has unit variance, i.e. the variance is equal to 1 and therefore also unit standard deviation. This function is symmetric around x equals 0, display style x equals 0, where it attains its maximum value 1 2 pi, display style 1 sqrt 2 pi, and has inflection points at x equals plus 1, display style x equals plus 1, and x equals minus 1, display style x equals minus 1. Authors differ on which normal distribution should be called the standard one. Gauss defined the standard normal as having variance sigma 2 equals 1 2, display style sigma caret 2 equals 1/2. That is phi x equals e minus x 2 pi, display style var phi x equals frac e caret x caret 2 sqrt pi. Stigler goes even further, defining the standard normal with variance sigma 2 equals 1 2 pi, display style sigma caret 2 equals 1 2 pi, phi x equals e minus pi x 2, display style var phi x equals e caret pi x caret 2. Topic: General normal distribution. Every normal distribution is a version of the standard normal distribution whose domain has been stretched by a factor sigma, display style sigma, the standard deviation, and then translated by mu, display style mu, the mean value f x mu sigma 2 equals 1 sigma phi x minus mu sigma, display style f x mid mu sigma caret 2 equals frac 1 sigma var phi left frac x mu sigma right. The probability density must be scaled by 1 sigma, display style 1 sigma, so that the integral is still 1. If z, display style z, is a standard normal deviate, then x equals sigma z plus mu, display style x equals sigma z plus mu, will have a normal distribution with expected value mu, display style mu, and standard deviation sigma, display style sigma. Conversely, if x display style x is a normal deviate with parameters mu display style mu and sigma 2 display style sigma caret 2, then z equals x minus mu sigma display style z equals x mu sigma will have a standard normal distribution. This variate is called the standardized form of x, x. Every normal distribution is the exponential of a quadratic function f x equals eax2 plus bx plus c. F x equals e caret x caret 2 plus bx plus c, where a 0 a and c equals b 4 a plus lane minus a pi 2 c equals b caret 2 4a plus lane a pi 2. In this form, the mean value is mu equals minus b 2 a display style mu equals b 2a, and the variance is sigma 2 equals minus 1 2 a display style sigma caret 2 equals minus 1 2a. For the standard normal distribution, a equals minus 1 2 display style equals minus 1/2, b equals 0 display style b equals 0, and c equals minus lane 2 pi 2 display style c equals lane 2 pi 2. Topic notation. The probability density of the standard Gaussian distribution, standard normal distribution with zero mean and unit variance, is often denoted with the Greek letter phi. Display style phi. Phi. The alternative form of the Greek letter phi. Phi. Display style var phi, is also used quite often. The normal distribution is often referred to as n mu sigma 2 display style n mu sigma caret 2 or n mu sigma 2 display style mathcal n mu sigma caret 2. Thus, when a random variable x display style x is distributed normally with mean mu display style mu and variance sigma 2 display style sigma caret 2, one may write x n mu sigma 2 display style x sim mathcal n mu sigma caret 2. Topic alternative parameterizations. Some authors advocate using the precision tau display style tau as the parameter defining the width of the distribution, instead of the deviation sigma display style sigma, or the variance sigma 2 display style sigma caret 2. The precision is normally defined as the reciprocal of the variance 1 sigma 2 display style 1 sigma caret 2. The formula for the distribution then becomes f x equals tau 2 pi e minus tau x minus mu 2 2 display style f x equals sqrt frac tau 2 pi e caret tau x mu caret 2 2. This choice is claimed to have advantages in numerical computations when sigma display style sigma is very close to zero and simplify formulas in some contexts, such as in the Bayesian inference of variables with multivariate normal distribution. Also the reciprocal of the standard deviation tau equals 1 sigma display style tau caret prime equals 1 sigma might be defined as the precision, and the expression of the normal distribution becomes f x equals tau 2 pi e minus tau 2 x minus mu 2 2. Display style f x equals frac tau caret prime sqrt 2 pi e caret tau caret prime caret 2 x mu caret 2 2. According to Stigler, this formulation is advantageous because of a much simpler and easier to remember formula, and simple approximate formulas for the quantiles of the distribution. Normal distributions form an exponential family with natural parameters theta 1 equals mu sigma 2 display style text style theta underscore 1 equals frac mu sigma caret 2 and theta 2 equals minus 1 2 sigma 2 display style text style theta underscore 2 equals frac minus 1 2 sigma caret 2 and natural statistics x and x2. The dual expectation parameters for normal distribution are eta 1. Topic mu and eta 2. Mu 2 plus sigma 2. Topic properties. The normal distribution is the only absolutely continuous distribution whose cumulants beyond the first two, i.e., other than the mean and variance, are zero. It is also the continuous distribution with the maximum entropy for a specified mean and variance. Geary has shown, assuming that the mean and variance are finite, that the normal distribution is the only distribution where the mean and variance calculated from a set of independent draws are independent of each other. The normal distribution is a subclass of the elliptical distributions. The normal distribution is symmetric about its mean, and is non-zero over the entire real line. As such, it may not be a suitable model for variables that are inherently positive or strongly skewed, such as the weight of a person or the price of a share. Such variables may be better described by other distributions, such as the log normal distribution or the Pareto distribution. The value of the normal distribution is practically zero when the value x x lies more than a few standard deviations away from the mean, e.g., a spread of 3 standard deviations covers all but 0.27% of the total distribution. Therefore, it may not be an appropriate model when one expects a significant fraction of outliers, values that lie many standard deviations away from the mean, and least squares and other statistical inference methods that are optimal for normally distributed variables often become highly unreliable when applied to such data. In those cases, a more heavy-tailed distribution should be assumed and the appropriate robust statistical inference methods applied. The Gaussian distribution belongs to the family of stable distributions which are the attractors of sums of independent, identically distributed distributions whether or not the mean or variance is finite. Except for the Gaussian, which is a limiting case, all stable distributions have heavy tails and infinite variance. It is one of the few distributions that are stable and that have probability density functions that can be expressed analytically, the others being the Cauchy distribution and the Levy distribution. Topic: symmetries and derivatives. The normal distribution with density f x f x mean mu mu and standard deviation sigma greater than 0 sigma greater than 0 has the following properties. It is symmetric around the point x equals mu x equals mu, which is at the same time the mode, the median and the mean of the distribution. It is unimodal. Its first derivative is positive for x mu, x negative for x greater than mu, x greater than mu, and 0 only at x equals mu. X equals mu. The area under the curve and over the x axis is unity, i.e., equal to 1. Its density has two inflection points where the second derivative of f is 0 and changes sign, located one standard deviation away from the mean, namely at x equals mu minus sigma x equals mu sigma and x equals mu plus sigma x equals mu plus sigma. Its density is log concave. Its density is infinitely differentiable, indeed supersmooth of order 2. Furthermore, the density phi var phi of the standard normal distribution, i.e. mu equals 0 mu equals 0 and sigma equals 1 sigma equals 1 also has the following properties. Its first derivative is phi x equals minus x phi x display style var phi caret prime x equals x var phi x. Its second derivative is phi x equals x 2 minus 1 phi x display style var phi caret prime x equals x caret 2 minus 1 var phi x. More generally, its nth derivative is phi n x equals minus 1 n he n x phi x display style var phi caret n x equals minus 1 caret n operator name he underscore n x var phi x, where he n x display style operator name he underscore n x is the nth probabilist Hermite polynomial. The probability that a normally distributed variable x display style x with known mu display style mu and sigma display style sigma is in a particular set can be calculated by using the fact that the fraction z equals x minus mu sigma display style z equals x mu sigma has a standard normal distribution. Topic: Moments. The plane and absolute moments of a variable x (x) are the expected values of x p (x p) and x p (x p) respectively. If the expected value mu mu of x x is 0, these parameters are called central moments. Usually we are interested only in moments with integer order p p. If x x has a normal distribution, these moments exist and are finite for any p p whose real part is greater than -1. For any non-negative integer p p, the plane central moments are exp equals 0 if p is odd, sigma p p-1 if p is even. Display style operator name left x p right equals begin cases 0 and text if p text is odd, sigma p p1 and text if p text is even end cases. Here n display style n denotes the double factorial, that is the product of all numbers from n display style n to 1 that have the same parity as n. Display style n, the central absolute moments coincide with plane moments for all even orders, but are non-zero for odd orders. For any non-negative integer p display style p e x p equals sigma p p minus 1 2 pi. If p is odd 1, if p is even equals sigma p 2p 2 gamma p plus 1 2 pi display style operator name left x p right equals sigma p p1 cdot left begin cases sqrt frac 2 pi and text if p text is odd 1 and text if p text is even end cases right equals sigma p cdot frac 2 p 2 gamma left frac p plus 1 2 right sqrt pi. The last formula is valid also for any non-integer p greater than -1. Display style p greater than -1 when the mean mu does not equal 0. Display style mu neq 0. The plane and absolute moments can be expressed in terms of confluent hypergeometric functions 1f1 display style _1 f_1 and u. Display style u e x p equals sigma p minus I 2 p u minus p 2 1 2 minus 1 2 mu sigma 2. Display style operator name left x p right equals sigma p cdot I sqrt 2 p u left frac p 2 frac 1 2 frac 1 2 left frac mu sigma right 2 right e x p equals sigma p 2 p 2 gamma 1 plus p 2 pi 1 f 1 minus p 2 1 2 minus 1 2 mu sigma 2. Display style operator name e left x caret p right equals sigma caret p c dot 2 caret p 2 frac gamma left frac 1 plus p 2 right sqrt pi underscore 1 f underscore 1 left frac p 2 frac 1 2 frac 1 2 left frac mu sigma right caret 2 right. These expressions remain valid even if p p is not integer. See also generalized Hermite polynomials. The expectation of x x conditioned on the event that x x lies in an interval a b a b is given by e x a x b equals mu minus sigma 2 f b minus f a f b minus f a display style operator name e left x mid aware f display style f and f display style f respectively are the density and the cumulative distribution function of x display style x. For b equals infinity display style b equals inft, this is known as the inverse Mills ratio. Note that above density f display style f of x display style x is used instead of standard normal density as in inverse Mills ratio. So here we have sigma 2 display style sigma caret 2 instead of sigma display style sigma. Topic: Fourier transform and characteristic function. The Fourier transform of a normal density f display style f with mean mu display style mu and standard deviation sigma display style sigma is f caret t equals minus infinity f x e minus I t x d x equals e minus I mu t e minus 1 2 sigma t 2 display style hat f t equals int underscore inft caret inft f x e caret I t x dx equals e caret I mu t e caret frac 1 2 sigma t caret 2, where I display style I is the imaginary unit. If the mean mu equals 0 display style mu equals 0, the first factor is 1 and the Fourier transform is, apart from a constant factor, a normal density on the frequency domain with mean 0 and standard deviation 1 sigma display style 1 sigma. In particular, the standard normal distribution phi display style var phi is an eigenfunction of the Fourier transform. In probability theory, the Fourier transform of the probability distribution of a real-valued random variable x (x) is closely connected to the characteristic function phi x t (var_phi_x of that variable, which is defined as the expected value of e I t x (e caret I t x) as a function of the real variable t (t), the frequency parameter of the Fourier transform. This definition can be analytically extended to a complex value variable t (t). The relation between both is phi x t equals f caret minus t (var_phi_x t equals hat f t). Topic: Moment and cumulant generating functions. The moment generating function of a real random variable x (x) is the expected value of e t x (e caret t x) as a function of the real parameter t (t). For a normal distribution with density f (f), mean mu (mu) and deviation sigma (sigma), the moment generating function exists and is equal to m t equals e t x equals f caret I t equals e mu t e 1 2 sigma 2 t 2 display style m t equals operator name e caret t x equals hat f it equals e caret mu t e caret t frac 1 2 sigma caret 2 t caret 2. The cumulant generating function is the logarithm of the moment generating function, namely g t equals lane m t equals mu t plus 1 2 sigma 2 t 2 display style g t equals lane m t equals mu t plus t frac 1 2 sigma caret 2 t caret 2. Since this is a quadratic polynomial in t display style t, only the first two cumulants are non-zero, namely the mean mu display style mu and the variance sigma 2 display style sigma caret 2. Topic: Cumulative distribution function. The cumulative distribution function (CDF) of the standard normal distribution, usually denoted with the capital Greek letter phi phi, is the integral phi x equals 1 2 pi minus infinity x e minus t 2 d t. Display style phi x equals frac 1 sqrt 2 pi int underscore inf t caret x e caret t caret 2 dt. The related error function erf x display style operator name erf x gives the probability of a random variable with normal distribution of mean 0 and variance 1/2 falling in the range minus x x display style x that is erf x equals 2 pi 0 x e minus t 2 d t. Display style operator name erf x equals frac 2 sqrt pi int underscore 0 caret x e caret t caret 2 dt. These integrals cannot be expressed in terms of elementary functions, and are often said to be special functions. However, many numerical approximations are known, see below. The two functions are closely related, namely phi x equals 1 2 1 plus erf x 2 display style phi x equals frac 1 2 left 1 plus operator name erf left frac x sqrt 2 right. For a generic normal distribution with density f display style f mean mu display style mu and deviation sigma display style sigma, the cumulative distribution function is f x equals phi x minus mu sigma equals 1 2 1 plus erf x minus mu sigma 2 display style f x equals phi left frac x mu sigma right equals frac 1 2 left 1 plus operator name erf left frac x mu sigma sqrt 2 right. The complement of the standard normal CDF q x equals 1 minus phi x display style q x equals 1 phi x is often called the Q function, especially in engineering texts. It gives the probability that the value of a standard normal random variable x display style x will exceed x display style x p x greater than x display style p x greater than x. Other definitions of the q display style q function, all of which are simple transformations of phi display style phi, are also used occasionally. The graph of the standard normal CDF phi display style phi has two-fold rotational symmetry around the point 0, 1/2, that is phi minus x equals 1 minus phi x display style phi x equals 1 phi x. Its antiderivative indefinite integral is phi x d x equals x phi x plus phi x plus c display style int phi x dx equals x phi x plus var phi x plus c. The CDF of the standard normal distribution can be expanded by integration by parts into a series phi x equals 1 2 plus 1 2 pi e minus x 2 2 x plus x 3 3 plus x 5 3 5 plus x 2 n plus 1 2 n plus 1 plus display style phi x equals frac 1 2 plus frac 1 sqrt 2 pi c dot e caret x caret 2 2 left x plus frac x caret 3 3 plus frac x caret 5 3 c dot 5 plus c dots plus frac x caret 2 n plus 1 2 n plus 1 plus c dots right, where display style denotes the double factorial. An asymptotic expansion of the CDF for large X can also be derived using integration by parts. See error function #asymptotic expansion. Topic: Standard deviation and coverage. About 68% of values drawn from a normal distribution are within one standard deviation sigma away from the mean, about 95% of the values lie within two standard deviations, and about 99.7% are within three standard deviations. This fact is known as the 68 to 95–99.7 empirical rule, or the 3 sigma rule. More precisely, the probability that a normal deviate lies in the range between mu minus n sigma display style mu n sigma and mu plus n sigma display style mu plus n sigma is given by f mu plus n sigma minus f mu minus n sigma equals phi n minus phi minus n equals ERF n 2. Display style f mu plus n sigma f mu n sigma equals phi n equals operator name ERF left frac n sqrt 2 right. To 12 significant figures, the values for n equals 1 2 6 display style n equals 1 2 l dots 6 r. Topic: Quantile function. The quantile function of a distribution is the inverse of the cumulative distribution function. The quantile function of the standard normal distribution is called the probit function, and can be expressed in terms of the inverse error function phi minus 1 p equals 2 erf minus 1 2 p minus 1 p element of 0 1 display style phi caret minus 1 p equals sqrt 2 operator name erf caret minus 1 2 p minus 1 quad p in 0 1 for a normal random variable with mean mu display style mu and variance sigma 2 display style sigma caret 2. The quantile function is f minus 1 p equals mu plus sigma phi minus 1 p equals mu plus sigma 2 erf minus 1 2 p minus 1 p element of 0 1 display style f caret minus 1 p equals mu plus sigma phi caret minus 1 p equals mu plus sigma sqrt 2 operator name erf caret minus 1 2 p minus 1 quad p in 0 1. The quantile phi minus 1 p display style phi caret minus 1 p of the standard normal distribution is commonly denoted as z p display style z underscore p. These values are used in hypothesis testing, construction of confidence intervals and QQ plots. A normal random variable x display style x will exceed mu plus z p sigma display style mu plus z underscore p sigma with probability 1 minus p display style 1 p and will lie outside the interval mu plus or minus z p sigma display style mu pmz underscore p sigma with probability 2 1 minus p display style 2 1 p. In particular, the quantile z 0.975 display style z underscore 0.975 is 1.96. Therefore, a normal random variable will lie outside the interval mu plus or minus 1.96 sigma display style mu pm 1.96 sigma in only 5% of cases. The following table gives the quantile z p display style z underscore p such that x display style x will lie in the range mu plus or minus z p sigma display style mu pmz underscore p sigma with a specified probability p display style p. These values are useful to determine tolerance interval for sample averages and other statistical estimators with normal or asymptotically normal distributions. Note, the following table shows 2 ERF minus 1 P equals phi minus 1 P plus 1 2 display style sqrt 2 operator name erf caret minus 1 p equals phi caret minus 1 left frac p plus 1 2 right not phi minus 1 p display style phi caret minus 1 p as defined above. For small p display style p, the quantile function has the useful asymptotic expansion phi minus 1 p equals minus lane 1 p 2 minus lane 1 p 2 minus lane 2 pi plus o 1 display style phi caret minus 1 p equals sqrt lane frac 1 p caret 2 lane frac 1 p caret 2 lane 2 pi plus math call o 1. Topic: Zero variance limit. In the limit when sigma display style sigma tends to 0, the probability density f x display style f x eventually tends to 0 at any x does not equal mu display style x neq mu, but grows without limit if x equals mu display style x equals mu while its integral remains equal to 1. Therefore, the normal distribution cannot be defined as an ordinary function when sigma equals 0 display style sigma equals 0. However, one can define the normal distribution with zero variance as a generalized function, specifically, as Dirac's delta function. Delta delta translated by the mean mu mu that is f x equals delta x minus mu display style f x equals delta x mu. Its CDF is then the Heaviside step function translated by the mean mu display style mu, namely f x equals 0 if x mu 1 if x mu display style f x equals begin cases 0 and text if x. Topic: Central limit theorem. The central limit theorem states that under certain fairly common conditions, the sum of many random variables will have an approximately normal distribution. More specifically, where x 1 x n display style x underscore 1 l dots x underscore n are independent and identically distributed random variables with the same arbitrary distribution, zero mean, and variance. Sigma 2 display style sigma caret 2 and z display style z is their mean scaled by n display style sqrt n z equals n 1 n I equals 1 n x I display style z equals sqrt n left frac 1 n sum underscore I equals 1 caret n x underscore I right. Then as n display style n increases, the probability distribution of z display style z will tend to the normal distribution with zero mean and variance. Sigma 2 display style sigma caret 2. The theorem can be extended to variables x I display style x underscore I that are not independent and or not identically distributed if certain constraints are placed on the degree of dependence and the moments of the distributions. Many test statistics, scores, and estimators encountered in practice contain sums of certain random variables in them, and even more estimators can be represented as sums of random variables through the use of influence functions. The central limit theorem implies that those statistical parameters will have asymptotically normal distributions. The central limit theorem also implies that certain distributions can be approximated by the normal distribution, for example, the binomial distribution b n p displaystyle b n p is approximately normal with mean n p displaystyle n p and variance n p 1 minus p display style n p 1 p for large n display style n and for p display style p not too close to 0 or 1. The Poisson distribution with parameter lambda display style lambda is approximately normal with mean lambda display style lambda and variance lambda display style lambda for large values of lambda display style lambda. The chi-squared distribution chi 2 k display style chi caret 2 k is approximately normal with mean k display style k and variance 2 k display style 2 k for large k display style k. The student's t distribution t nu display style t nu is approximately normal with mean 0 and variance 1 when nu display style nu is large. Whether these approximations are sufficiently accurate depends on the purpose for which they are needed, and the rate of convergence to the normal distribution. It is typically the case that such approximations are less accurate in the tails of the distribution. A general upper bound for the approximation error in the central limit theorem is given by the Berry-Esseen theorem. Improvements of the approximation are given by the Edgeworth expansions. Topic: Maximum entropy. Of all probability distributions over the reals with a specified mean mu display style mu and variance sigma 2 display style sigma caret 2, the normal distribution n mu sigma 2 display style n mu sigma caret 2 is the one with maximum entropy. If x display style x is a continuous random variable with probability density f x display style f x, then the entropy of x display style x is defined as h x equals minus infinity f x log f x d x equals 1 2 1 plus log 2 sigma 2 pi display style h x equals int underscore inf t caret inf t f x log f x dx equals tfrac 1 2 1 plus log 2 sigma caret 2 pi, where f x log f x display style f x log f x is understood to be 0 whenever f x equals 0 display style f x equals 0. This functional can be maximized, subject to the constraints that the distribution is properly normalized and has a specified variance, by using variational calculus. A function with two Lagrange multipliers is defined L equals minus infinity f x lane f x d x minus lambda 0 1 minus infinity f x d x minus lambda sigma 2 minus infinity f x x minus mu 2 d x display style L equals int underscore inf t caret inf t f x lane f x dx lambda underscore 0 left 1 int underscore inf t caret inf t f x dx right lambda left sigma caret 2 int underscore inf t caret inf t f x x mu caret 2 dx right, where f x display style f x is for now regarded as some density function with mean mu display style mu and standard deviation sigma display style sigma. At maximum entropy, a small variation delta f x display style delta f x about f x display style f x will produce a variation delta L display style delta L about L display style L, which is equal to 0 equals delta L equals minus infinity delta f x lane f x plus 1 plus lambda 0 plus lambda x minus mu 2 d x display style 0 equals delta L equals int underscore inft caret inft delta f x left lane f x plus 1 plus lambda underscore 0 plus lambda x mu caret 2 right dx. Since this must hold for any small delta f x display style delta f x, the term in brackets must be 0, and solving for f x display style f x yields f x equals e minus lambda 0 minus 1 minus lambda x minus mu 2 display style f x equals e caret lambda underscore 0 minus 1 lambda x mu caret 2. Using the constraint equations to solve for lambda 0 display style lambda underscore 0 and lambda display style lambda yields the density of the normal distribution f x mu sigma equals 1 2 pi sigma 2 e minus x minus mu 2 sigma 2 display style f x mu sigma equals frac 1 sqrt 2 pi sigma caret 2 e caret frac x mu caret 2 sigma caret 2. Topic: Operations on normal deviates. The family of normal distributions is closed under linear transformations, if X is normally distributed with mean mu and standard deviation sigma, then the variable y equals x plus b, for any real numbers a and b, is also normally distributed, with mean a mu plus b and standard deviation, a, sigma. Also if x1 and x2 are two independent normal random variables, with means mu1, mu2 and standard deviation sigma1, sigma2, then their sum x1 plus x2 will also be normally distributed, proof, with mean mu1 plus mu2 and variance sigma 1 2 plus sigma 2 2 display style sigma underscore 1 caret 2 plus sigma underscore 2 caret 2. In particular, if x and y are independent normal deviates with zero mean and variance sigma 2, then x plus y and x minus y are also independent and normally distributed, with zero mean and variance 2 sigma 2. This is a special case of the polarization identity. Also, if x1, x2 are two independent normal deviates with mean mu and deviation sigma, and a, b are arbitrary real numbers, then the variable x3 equals a x1 plus b x2 minus a plus b mu a 2 plus b 2 plus mu display style x underscore 3 equals frac x underscore 1 plus bx underscore 2 a plus b mu sqrt a caret 2 plus b caret 2 plus mu is also normally distributed with mean mu and deviation sigma. It follows that the normal distribution is stable with exponent alpha equals 2. More generally, any linear combination of independent normal deviates is a normal deviate. Topic: Infinite divisibility and Cramér's theorem. For any positive integer n, any normal distribution with mean mu and variance sigma 2 is the distribution of the sum of n independent normal deviates, each with mean mu n and variance sigma 2 n. This property is called infinite divisibility. Conversely, if x1 and x2 are independent random variables and their sum x1 plus x2 has a normal distribution, then both x1 and x2 must be normal deviates. This result is known as Cramér's decomposition theorem, and is equivalent to saying that the convolution of two distributions is normal if and only if both are normal. Cramér's theorem implies that a linear combination of independent non-Gaussian variables will never have an exactly normal distribution, although it may approach it arbitrarily closely. Bernstein's theorem. Bernstein's theorem states that if x and y are independent and x plus y and x minus y are also independent, then both x and y must necessarily have normal distributions. More generally, if x1 xn are independent random variables, then two distinct linear combinations akxk and bkxk will be independent if and only if all xk's are normal and akbk sigma 2k equals 0, where sigma 2k denotes the variance of xk. Other properties. Related distributions. Operations on a single random variable. If x is distributed normally with mean mu and variance sigma 2, then the exponential of x is distributed log normally, x tilde lane n mu sigma 2. The absolute value of x has folded normal distribution x tilde nf mu sigma 2. If mu equals 0, this is known as the half-normal distribution. The absolute value of normalized residuals, x minus mu, sigma, has chi distribution with 1 degree of freedom, x minus mu, sigma tilde chi 1, x minus mu, sigma. The square of x, sigma has the noncentral chi-squared distribution with 1 degree of freedom, x2, sigma 2 tilde chi 21, mu 2, sigma 2. If mu equals 0, the distribution is called simply chi-squared. The distribution of the variable x restricted to an interval a, b is called the truncated normal distribution. X minus mu minus 2 has a Lévy distribution with location 0 and scale sigma minus 2. Topic: Combination of two independent random variables. If x1 and x2 are two independent standard normal random variables with mean 0 and variance 1, then their sum and difference is distributed normally with mean 0 and variance 2, x1 plus or minus x2 0, 2. Their product z. X1 x2 follows the product normal distribution with density function f z z pi minus 1 k0 z, where k0 is the modified Bessel function of the second kind. This distribution is symmetric around 0, unbounded at z. 0, and has the characteristic function phi z t 1 plus t2 minus 1/2. Their ratio follows the standard Cauchy distribution, x1, x2 Cauchy 0, 1. Their Euclidean norm x 1 2 plus x 2 2 display style sqrt x underscore 1 caret 2 plus x underscore 2 caret 2 has the Rayleigh distribution. Topic: Combination of two or more independent random variables. If x1, x2, xn are independent standard normal random variables, then the sum of their squares has the chi-squared distribution with n degrees of freedom. X 1 2 plus x n 2 chi n 2 display style x underscore 1 caret 2 plus c dots plus x underscore n caret 2 sim chi underscore n caret 2. If x1, x2, xn are independent normally distributed random variables with means mu and variances sigma 2, then their sample mean is independent from the sample standard deviation, which can be demonstrated using Bossu's theorem or Cochrane's theorem. The ratio of these two quantities will have the student's t distribution with n-1 degree of freedom t equals x minus mu s n equals 1 n x 1 plus x n minus mu 1 n n minus 1 x 1 minus x 2 plus x n minus x 2 t n minus 1. Display style t equals frac overline x mu s sqrt n equals frac 1 n x underscore 1 plus c dots plus x underscore n mu sqrt frac 1 n n 1 left x underscore 1 overline x caret 2 plus c dots plus x underscore n overline x caret 2 right sim t underscore n1 if x1 xn y1 ym are independent standard normal random variables, then the ratio of their normalized sums of squares will have the F distribution with n m degrees of freedom. F equals x 1 2 plus x 2 2 plus x n 2 n y 1 2 plus y 2 2 plus y m 2 m f n m. Display style f equals frac left x underscore 1 caret 2 plus x underscore 2 caret 2 plus c dots plus x underscore n caret 2 right n left y underscore 1 caret 2 plus y underscore 2 caret 2 plus c dots plus y underscore m caret 2 right per meter sim f underscore n m. Topic: Operations on the density function. The split normal distribution is most directly defined in terms of joining scaled sections of the density functions of different normal distributions and rescaling the density to integrate to one. The truncated normal distribution results from rescaling a section of a single density function. Extensions. The notion of normal distribution, being one of the most important distributions in probability theory, has been extended far beyond the standard framework of the univariate, that is one-dimensional case 1. All these extensions are also called normal or Gaussian laws, so a certain ambiguity in names exists. The multivariate normal distribution describes the Gaussian law in the k-dimensional Euclidean space. A vector x element of Rk is multivariate normally distributed if any linear combination of its components kj equals 1 ajxj has a univariate normal distribution. The variance of X is AK times K symmetric positive definite matrix V. The multivariate normal distribution is a special case of the elliptical distributions. As such, its isodensity loci in the k equals 2 case are ellipses and in the case of arbitrary k are ellipsoids. Rectified Gaussian distribution. A rectified version of normal distribution with all the negative elements reset to zero. Complex normal distribution deals with the complex normal vectors. A complex vector x element of Ck is said to be normal if both its real and imaginary components jointly possess a 2k-dimensional multivariate normal distribution. The variance-covariance structure of X is described by two matrices, the variance matrix gamma, and the relation matrix C. Matrix normal distribution describes the case of normally distributed matrices. Gaussian processes are the normally distributed stochastic processes. These can be viewed as elements of some infinite-dimensional Hilbert space H, and thus are the analogues of multivariate normal vectors for the case k equals infinity. A random element H element of H is said to be normal if for any constant A element of H the scalar product A, H has a univariate normal distribution. The variance structure of such Gaussian random element can be described in terms of the linear covariance operator K, H. Several Gaussian processes became popular enough to have their own names: Brownian motion, Brownian bridge, Ornstein-Uhlenbeck process. Gaussian Q distribution is an abstract mathematical construction that represents a Q analog of the normal distribution. The Q Gaussian is an analog of the Gaussian distribution, in the sense that it maximizes the Salis entropy, and is one type of Salis distribution. Note that this distribution is different from the Gaussian Q distribution above. A random variable x has a two-piece normal distribution if it has a distribution f x x equals n mu sigma 1 2 if x mu display style f underscore x x equals n mu sigma underscore 1 caret 2 text if x leq mu f x x equals n mu sigma 2 2 if x mu display style f underscore x x equals n mu sigma underscore 2 caret 2 text if x geq mu, where mu is the mean and sigma 1 and sigma 2 are the standard deviations of the distribution to the left and right of the mean respectively. The mean, variance and third central moment of this distribution have been determined. E x equals mu plus 2 pi sigma 2 minus sigma 1. Display style operator name E x equals mu plus sqrt frac 2 pi sigma underscore 2 sigma underscore 1 v x equals 1 minus 2 pi sigma 2 minus sigma 1 2 plus sigma 1 sigma 2. Display style operator name v x equals left 1 frac 2 pi right sigma underscore 2 sigma underscore 1 caret 2 plus sigma underscore 1 sigma underscore 2 t x equals 2 pi sigma 2 minus sigma 1 4 pi minus 1 sigma 2 minus sigma 1 2 plus sigma 1 sigma 2. Display style operator name T x equals sqrt frac 2 pi sigma underscore 2 sigma underscore 1 left frac 4 pi minus 1 right sigma underscore 2 sigma underscore 1 caret 2 plus sigma underscore 1 sigma underscore 2 right. where E x, V x, and T x are the mean, variance, and third central moment respectively. One of the main practical uses of the Gaussian law is to model the empirical distributions of many different random variables encountered in practice. In such case, a possible extension would be a richer family of distributions, having more than two parameters and therefore being able to fit the empirical distribution more accurately. The examples of such extensions are Pearson distribution, a four-parameter family of probability distributions that extend the normal law to include different skewness and kurtosis values. The generalized normal distribution, also known as the exponential power distribution, allows for distribution tails with thicker or thinner asymptotic behaviors. Normality tests. Normality tests assess the likelihood that the given dataset x1 xn comes from a normal distribution. Typically, the null hypothesis H0 is that the observations are distributed normally with unspecified mean mu and variance sigma 2, versus the alternative Ha that the distribution is arbitrary. Many tests over 40 have been devised for this problem, the more prominent of them are outlined below. Visual tests are more intuitively appealing but subjective at the same time, as they rely on informal human judgment to accept or reject the null hypothesis. QQ-plot is a plot of the sorted values from the data set against the expected values of the corresponding quantiles from the standard normal distribution. That is, it's a plot of point of the form phi-1 pk x k, where plotting points pk are equal to pk equals k minus alpha, n plus 1 minus 2 alpha, and alpha is an adjustment constant, which can be anything between 0 and 1. If the null hypothesis is true, the plotted points should approximately lie on a straight line. PP-plot, similar to the QQ plot, but used much less frequently. This method consists of plotting the points phi z k p k, where z k equals x k minus mu caret sigma caret display style text style z underscore k equals x underscore k hat mu hat sigma. For normally distributed data, this plot should lie on a 45 degrees line between 0, 0 and 1, 1. Shapiro-Wilk test employs the fact that the line in the QQ plot has the slope of sigma. The test compares the least squares estimate of that slope with the value of the sample variance, and rejects the null hypothesis if these two quantities differ significantly. Normal probability plot, Rankit plot, moment tests, D'Agostino's k-squared test, Jark-Bara test, empirical distribution function tests, Lilliefors test, an adaptation of the Kolmogorov-Smirnov test, Anderson-Darling test. Topic: Estimation of parameters. It is often the case that we don't know the parameters of the normal distribution, but instead want to estimate them. That is, having a sample x1 xn from a normal n mu sigma 2 population, we would like to learn the approximate values of parameters mu and sigma 2. The standard approach to this problem is the maximum likelihood method, which requires maximization of the log likelihood function lane L mu sigma 2 equals I equals 1 n lane f x I mu sigma 2 equals minus north 2 lane 2 pi minus north 2 lane sigma 2 minus 1 2 sigma 2 I equals 1 n x I minus mu 2. Display style lane math call L mu sigma caret 2 equals sum underscore I equals 1 caret n lane f x underscore I mid mu sigma caret 2 equals frac north 2 lane 2 pi frac north 2 lane sigma caret 2 frac 1 2 sigma caret 2 sum underscore I equals 1 caret n x underscore I mu caret 2. Taking derivatives with respect to mu and sigma 2 and solving the resulting system of first-order conditions yields the maximum likelihood estimates mu caret equals x 1 n I equals 1 n x I sigma caret 2 equals 1 n I equals 1 n x I minus x 2. Display style hat mu equals overline x equiv frac 1 n sum underscore I equals 1 caret n x underscore I q quad hat sigma caret 2 equals frac 1 n sum underscore I equals 1 caret n x underscore I overline x caret 2. Topic: Sample mean. Estimator mu caret display style text style hat mu is called the sample mean since it is the arithmetic mean of all observations. The statistic x display style text style overline x is complete and sufficient for mu, and therefore by the Lehmann-Scheffé theorem mu caret display style text style hat mu is the uniformly minimum variance unbiased UMVU estimator. In finite samples it is distributed normally mu caret n mu sigma 2 n display style hat mu sim math call n mu sigma caret 2 n. The variance of this estimator is equal to the element of the inverse Fisher information matrix I minus 1 display style text style math call I caret minus 1. This implies that the estimator is finite sample efficient. Of practical importance is the fact that the standard error of mu caret display style text style hat mu is proportional to 1 n display style text style 1 sqrt n. That is, if one wishes to decrease the standard error by a factor of 10, one must increase the number of points in the sample by a factor of 100. This fact is widely used in determining sample sizes for opinion polls and the number of trials in Monte Carlo simulations. From the standpoint of the asymptotic theory, mu caret display style text style hat mu is consistent, that is, it converges in probability to mu as n infinity. The estimator is also asymptotically normal, which is a simple corollary of the fact that it is normal in finite samples n mu caret minus mu d n 0 sigma 2. Display style sqrt n hat mu x right arrow d math call n 0 sigma caret 2. Topic: Sample variance. The estimator sigma caret 2 display style text style hat sigma caret 2 is called the sample variance, since it is the variance of the sample x1 xn. In practice, another estimator is often used instead of the sigma caret 2 display style text style hat sigma caret 2. This other estimator is denoted S2, and is also called the sample variance, which represents a certain ambiguity in terminology. Its square root S is called the sample standard deviation. The estimator S2 differs from sigma caret 2 display style text style hat sigma caret 2 by having n-1 instead of n in the denominator, the so-called Bessel's correction. S2 equals n minus 1 sigma caret 2 equals 1 n minus 1 I equals 1 n x I minus x 2. Display style s caret 2 equals frac n 1 hat sigma caret 2 equals frac 1 n1 sum underscore I equals 1 caret n x underscore I overline x caret 2. The difference between s2 and sigma caret 2 display style text style hat sigma caret 2 becomes negligibly small for large n's. In finite samples, however, the motivation behind the use of S2 is that it is an unbiased estimator of the underlying parameter sigma 2, whereas sigma caret 2 display style text style hat sigma caret 2 is biased. Also, by the Lehmann-Scheffé theorem, the estimator S2 is uniformly minimum variance unbiased (UMVU), which makes it the best estimator among all unbiased ones. However, it can be shown that the biased estimator sigma caret 2 display style text style hat sigma caret 2 is better than the S2 in terms of the mean squared error (MSE) criterion. In finite samples, both S2 and sigma caret 2 display style text style hat sigma caret 2 have scaled chi-squared distribution with n-1 degrees of freedom. S2 sigma 2 n minus 1 chi n minus 1 2 sigma caret 2 sigma 2 n chi n minus 1 2 display style s caret 2 sim frac sigma caret 2 n1 c dot chi underscore n1 caret 2 q quad hat sigma caret 2 sim frac sigma caret 2 n c dot chi underscore n1 caret 2. The first of these expressions shows that the variance of S2 is equal to 2 sigma 4 n-1, which is slightly greater than the SS element of the inverse Fisher information matrix. I minus 1 display style text style math call I caret minus 1. Thus, S2 is not an efficient estimator for sigma 2, and moreover, since S2 is UMVU, we can conclude that the finite sample efficient estimator for sigma 2 does not exist. Applying the asymptotic theory, both estimators S2 and sigma caret 2 display style text style hat sigma caret 2 are consistent, that is, they converge in probability to sigma 2 as the sample size n infinity. The two estimators are also both asymptotically normal. N sigma caret 2 minus sigma 2 n s 2 minus sigma 2 d n 0 2 sigma 4 display style sqrt n hat sigma caret 2 sigma caret 2 simic sqrt n s caret 2 sigma caret 2 x right arrow d math call n 0 2 sigma caret 4. In particular, both estimators are asymptotically efficient for sigma 2. Topic: Confidence intervals. By Cochran's theorem, for normal distributions the sample mean mu caret display style text style hat mu and the sample variance S2 are independent, which means there can be no gain in considering their joint distribution. There is also a converse theorem: if in a sample the sample mean and sample variance are independent, then the sample must have come from the normal distribution. The independence between mu caret display style text style hat mu and S can be employed to construct the so-called T statistic. T equals mu caret minus mu S n equals x minus mu 1 n n minus 1 x I minus x 2 t n minus 1. Display style T equals frac hat mu S sqrt n equals frac overline x mu sqrt frac 1 n n1 sum x underscore I overline x caret 2 sim T underscore n1. This quantity T has the student's T distribution with n-1 degrees of freedom, and it is an ancillary statistic independent of the value of the parameters. Inverting the distribution of this t-statistics will allow us to construct the confidence interval for μ. Similarly, inverting the chi-2 distribution of the statistic S2 will give us the confidence interval for sigma 2 μ element of μ caret minus t n minus 1 1 minus alpha 2 1 n s mu caret plus t n minus 1 1 minus alpha 2 1 n s approximately equals mu caret minus z alpha 2 1 n s mu caret plus z alpha 2 1 n s display style mu in left hat mu t underscore n1 1 alpha 2 frac 1 sqrt n s hat mu plus t underscore n1 1 alpha 2 frac 1 sqrt n s right approximately left hat mu z underscore alpha 2 frac 1 sqrt n s hat mu plus z underscore alpha 2 frac 1 sqrt n s right sigma 2 element of n minus 1 s 2 chi n minus 1 1 minus alpha 2 2 n minus 1 s 2 chi n minus 1 alpha 2 2 approximately equals s 2 minus z alpha 2 2 n s 2 s 2 plus z alpha 2 2 n s 2 display style sigma caret 2 in left frac n1 s caret 2 chi underscore n1 1 alpha 2 caret 2 frac n1 s caret 2 chi underscore n1 alpha 2 caret 2 right approximately left s caret 2 z underscore alpha 2 frac sqrt 2 sqrt n s caret 2 s caret 2 plus z underscore alpha 2 frac sqrt 2 sqrt n s caret 2 right, where tk, p and chi2k, p are the pth quantiles of the t and chi2 distributions respectively. These confidence intervals are of the confidence level 1-alpha, meaning that the true values μ and sigma 2 fall outside of these intervals with probability or significance level alpha. In practice, people usually take alpha equals 5%, resulting in the 95% confidence intervals. The approximate formulas in the display above were derived from the asymptotic distributions of μ caret display style text style hat μ and s2. The approximate formulas become valid for large values of n, and are more convenient for the manual calculation since the standard normal quantiles z alpha 2 do not depend on n. In particular, the most popular value of alpha 5% results in z 0.025. 1.96. Bayesian analysis of the normal distribution. Bayesian analysis of normally distributed data is complicated by the many different possibilities that may be considered. Either the mean, or the variance, or neither, may be considered a fixed quantity. When the variance is unknown, analysis may be done directly in terms of the variance, or in terms of the precision, the reciprocal of the variance. The reason for expressing the formulas in terms of precision is that the analysis of most cases is simplified. Both univariate and multivariate cases need to be considered. Either conjugate or improper prior distributions may be placed on the unknown variables. An additional set of cases occurs in Bayesian linear regression, where in the basic model the data is assumed to be normally distributed, and normal priors are placed on the regression coefficients. The resulting analysis is similar to the basic cases of independent identically distributed data, but more complex. The formulas for the nonlinear regression cases are summarized in the conjugate prior article. Sum of two quadratics. Scalar form. The following auxiliary formula is useful for simplifying the posterior update equations, which otherwise become fairly tedious. A x minus y 2 plus b x minus z 2 equals a plus b x minus a y plus b z a plus b 2 plus a b a plus b y minus z 2. Display style a x y caret 2 plus b x z caret 2 equals a plus b left x frac I plus b z a plus b right caret 2 plus frac ab a plus b y z caret 2. This equation rewrites the sum of two quadratics in X by expanding the squares, grouping the terms in X, and completing the square. Note the following about the complex constant factors attached to some of the terms. The factor a y plus b z a plus b display style frac I plus b z a plus b has the form of a weighted average of y and z. A b a plus b equals 1 1 a plus 1 b equals a minus 1 plus b minus 1 minus 1. Display style frac ab a plus b equals frac 1 a plus frac 1 b equals a caret minus 1 plus b caret minus 1 caret minus 1. This shows that this factor can be thought of as resulting from a situation where the reciprocals of quantities a and b add directly, so to combine a and b themselves, it's necessary to reciprocate, add, and reciprocate the result again to get back into the original units. This is exactly the sort of operation performed by the harmonic mean, so it is not surprising that a b a plus b display style frac ab a plus b is 1/2 the harmonic mean of a and b. Topic: Vector form. A similar formula can be written for the sum of two vector quadratics, if x, y, z are vectors of length k, and a and b are symmetric, invertible matrices of size k times k displaystyle k times k, then y minus x a y minus x plus x minus z b x minus z equals x minus c a plus b x minus c plus y minus z a minus 1 plus b minus 1 minus 1 y minus z display style begin aligned and math bf y math bf x math bf a math bf y math bf x plus math bf x math bf z math bf b math bf x math bf z equals and math bf x math bf c math bf a plus math bf b math bf x math bf c plus math bf y math bf z math bf a caret minus 1 plus math bf b caret minus 1 caret minus 1 math bf y math bf z end aligned where c equals a plus b minus 1 a y plus b z display style math bf c equals math bf a plus math bf b caret minus 1 math bf a math bf y plus math bf b math bf z. Note that the form x ax is called a quadratic form and is a scalar x ax equals I j a I j x I x j display style math bf x math bf a math bf x equals sum underscore I j a underscore I j x underscore I x underscore j. In other words, it sums up all possible combinations of products of pairs of elements from X, with a separate coefficient for each. In addition, since x I x j equals x j x I display style x underscore I x underscore j equals x underscore j x underscore I, only the sum a I j plus a j I display style a underscore I j plus a underscore g matters for any off-diagonal elements of A, and there is no loss of generality in assuming that A is symmetric. Furthermore, if A is symmetric, then the form x a y equals y a x. Display style math BF x math BF a math BF y equals math BF y math BF a math BF x. Topic: Sum of differences from the mean. Another useful formula is as follows: I equals 1 n x I minus mu 2 equals I equals 1 n x I minus x 2 plus n x minus mu 2. Display style sum underscore I equals 1 caret n x underscore I mu caret 2 equals sum underscore I equals 1 caret n x underscore I bar x caret 2 plus n bar x mu caret 2, where x equals 1 n I equals 1 n x I. Display style bar x equals frac 1 n sum underscore I equals 1 caret n x underscore I. Topic: With known variance. For a set of d, normally distributed data points x of size n where each individual point x follows x n mu sigma 2 display style x sim math call n mu sigma caret 2. With known variance sigma 2, the conjugate prior distribution is also normally distributed. This can be shown more easily by rewriting the variance as the precision, i.e. using tau equals 1, sigma 2. Then if x n mu 1 tau display style x sim math call n mu 1 tau and mu n mu 0 1 tau 0 display style mu sim math call n mu underscore 0 1 tau underscore 0. We proceed as follows. First, the likelihood function is using the formula above for the sum of differences from the mean p x mu tau equals I equals 1 n tau 2 pi exp minus 1 2 tau x I minus mu 2 equals tau 2 pi n 2 exp minus 1 2 tau I equals 1 n x I minus mu 2 equals tau 2 pi n 2 exp minus 1 2 tau I equals 1 n xi minus x 2 plus n x minus mu 2. Display style begin aligned p math BF x mid mu tau and equals prod underscore I equals 1 caret n sqrt frac tau 2 pi exp left frac 1 2 tau x underscore I mu caret 2 right and equals left frac tau 2 pi right caret n 2 exp left frac 1 2 tau sum underscore I equals 1 caret n x underscore I mu caret 2 right and equals left frac tau 2 pi right caret n 2 exp left frac 1 2 tau left sum underscore I equals 1 caret n x underscore I bar x caret 2 plus n bar x mu caret 2 right end aligned. Then, we proceed as follows: p mu x p x mu p mu equals tau 2 pi n 2 exp minus 1 2 tau I equals 1 n x I minus x 2 plus n x minus mu 2 tau 0 2 pi exp minus 1 2 tau 0 mu minus mu 0 2 exp minus 1 2 tau I equals 1 n x I minus x 2 plus n x minus mu 2 plus tau 0 mu minus mu 0 2 exp minus 1 2 n tau x minus mu 2 plus tau 0 mu minus mu 0 2 equals exp minus 1 2 n tau plus tau 0 mu minus n tau x plus tau 0 mu 0 n tau plus tau 0 2 plus n tau 0 n tau plus tau 0 x minus mu 0 2 exp minus 1 2 n tau plus tau 0 mu minus n tau x plus tau 0 mu 0 n tau plus tau 0 2 display style begin aligned p mu mid math bf x and propto p math bf x mid mu p mu and equals left frac tau 2 pi right caret n 2 exp left frac 1 2 tau left sum underscore I equals 1 caret n x underscore I bar x caret 2 plus n bar x mu caret 2 right sqrt frac tau underscore 0 2 pi exp left frac 1 2 tau underscore 0 mu underscore 0 caret 2 right and propto exp left frac 1 2 left tau left sum underscore I equals 1 caret n x underscore I bar x caret 2 plus n bar x mu caret 2 right plus tau underscore 0 mu underscore 0 caret 2 right and propto exp left frac 1 2 left n tau bar x mu caret 2 plus tau underscore 0 mu underscore 0 caret 2 right and equals exp left frac 1 2 n tau plus tau underscore 0 left mu dfrac n tau bar x plus tau underscore 0 mu underscore 0 n tau plus tau underscore 0 right caret 2 plus frac n tau underscore 0 n tau plus tau underscore 0 bar x mu underscore 0 caret 2 right and propto exp left frac 1 2 n tau plus tau underscore 0 left mu dfrac n tau bar x plus tau underscore 0 mu underscore 0 n tau plus tau underscore 0 right caret 2 right end aligned. In the above derivation, we used the formula above for the sum of two quadratics and eliminated all constant factors not involving mu. The result is the kernel of a normal distribution, with mean n tau x plus tau 0 mu 0 n tau plus tau 0 display style frac n tau bar x plus tau underscore 0 mu underscore 0 n tau plus tau underscore 0 and precision n tau plus tau 0 display style n tau plus tau underscore 0, i.e. P mu x n tau x plus tau 0 mu 0 n tau plus tau 0 1 n tau plus tau 0 display style p mu mid math bf x sim math call n left frac n tau bar x plus tau underscore 0 mu underscore 0 n tau plus tau underscore 0 frac 1 n tau plus tau underscore 0 right. This can be written as a set of Bayesian update equations for the posterior parameters in terms of the prior parameters. Tau 0 equals tau 0 plus n tau mu 0 equals n tau x plus tau 0 mu 0 n tau plus tau 0 x equals 1 n I equals 1 n x I display style begin aligned tau underscore 0 and equals tau underscore 0 plus n tau mu underscore 0 and equals frac n tau bar x plus tau underscore 0 mu underscore 0 n tau plus tau underscore 0 ba R x and equals frac 1 n sum underscore I equals 1 caret n x underscore I end aligned, that is, to combine n data points with total precision of n tau or equivalently total variance of n sigma 2 and mean of values x display style bar x derive a new total precision simply by adding the total precision of the data to the prior total precision and form a new mean through a precision weighted average, i.e. a weighted average of the data mean and the prior mean, each weighted by the associated total precision. This makes logical sense if the precision is thought of as indicating the certainty of the observations. In the distribution of the posterior mean, each of the input components is weighted by its certainty, and the certainty of this distribution is the sum of the individual certainties. For the intuition of this, compare the expression the whole is or is not greater than the sum of its parts. In addition, consider that the knowledge of the posterior comes from a combination of the knowledge of the prior and likelihood, so it makes sense that we are more certain of it than of either of its components. The above formula reveals why it is more convenient to do Bayesian analysis of conjugate priors for the normal distribution in terms of the precision. The posterior precision is simply the sum of the prior and likelihood precisions, and the posterior mean is computed through a precision-weighted average, as described above. The same formulas can be written in terms of variance by reciprocating all the precisions, yielding the more ugly formulas sigma 0 2 equals 1 n sigma 2 plus 1 sigma 0 2 mu 0 equals n x sigma 2 plus mu 0 sigma 0 2 n sigma 2 plus 1 sigma 0 2 x equals 1 n I equals 1 nxi display style begin aligned sigma underscore 0 caret 2 and equals frac 1 frac n sigma caret 2 plus frac 1 sigma underscore 0 caret 2 mu underscore 0 and equals frac n bar x sigma caret 2 plus frac mu underscore 0 sigma underscore 0 caret 2 frac n sigma caret 2 plus frac 1 sigma underscore 0 caret 2 bar x and equals frac 1 n sum underscore I equals 1 caret n x underscore I end aligned. Topic with known mean. For a set of d, normally distributed data points x of size n where each individual point x follows x n mu sigma 2 display style x sim math call n mu sigma caret 2. With known mean mu, the conjugate prior of the variance has an inverse gamma distribution or a scaled inverse chi-squared distribution. The two are equivalent except for having different parameterizations. Although the inverse gamma is more commonly used, we use the scaled inverse chi squared for the sake of convenience. The prior for sigma 2 is as follows: p sigma 2 nu 0 sigma 0 2 equals sigma 0 2 nu 0 2 nu 0 2 gamma nu 0 2 exp minus nu 0 sigma 0 2 2 sigma 2 sigma 2 1 plus nu 0 2 exp minus nu 0 sigma 0 2 2 sigma 2 sigma 2 1 plus nu 0 2. Display style p sigma caret 2 mid nu underscore 0 sigma underscore 0 caret 2 equals frac sigma underscore 0 caret 2 frac nu underscore 0 2 caret nu underscore 0 2 gamma left frac nu underscore 0 2 right tilde frac exp left frac nu underscore 0 sigma underscore 0 caret 2 2 sigma caret 2 right sigma caret 2 caret 1 plus frac nu underscore 0 2 propto frac exp left frac nu underscore 0 sigma underscore 0 caret 2 2 sigma caret 2 right sigma caret 2 caret 1 plus frac nu underscore 0 2. The likelihood function from above, written in terms of the variance, is p x mu sigma 2 equals 1 2 pi sigma 2 n 2 exp minus 1 2 sigma 2 I equals 1 n x I minus mu 2 equals 1 2 pi sigma 2 n 2 exp minus s 2 sigma 2. Display style begin aligned p math bf x mid mu sigma caret 2 and equals left frac 1 2 p I sigma caret 2 right caret n 2 exp left frac 1 2 sigma caret 2 sum underscore I equals 1 caret n x underscore I mu caret 2 right and equals left frac 1 2 pi sigma caret 2 right caret n 2 exp left frac s 2 sigma caret 2 right end aligned where s equals I equals 1 n x I minus mu 2 display style s equals sum underscore I equals 1 caret n x underscore I mu caret 2. Then p sigma 2 x p x sigma 2 p sigma 2 equals 1 2 pi sigma 2 n 2 exp minus s 2 sigma 2 sigma 0 2 nu 0 2 nu 0 2 gamma nu 0 2 exp minus nu 0 sigma 0 2 2 sigma 2 sigma 2 1 plus nu 0 2 1 sigma 2 n 2 1 sigma 2 1 plus nu 0 2 exp minus s 2 sigma 2 plus minus nu 0 sigma 0 2 2 sigma 2 equals 1 sigma 2 1 plus nu 0 plus n 2 exp minus nu 0 sigma o 2 plus s 2 sigma 2 display style begin aligned p sigma caret 2 mid math bf x and propto p math bf x mid sigma caret 2 p sigma caret 2 and equals left frac 1 2 pi sigma caret 2 right caret n 2 exp left frac s 2 sigma caret 2 right frac sigma underscore 0 caret 2 frac nu underscore 0 2 caret frac nu underscore 0 2 gamma left frac nu underscore 0 2 right tilde frac exp left frac nu underscore 0 sigma underscore 0 caret 2 2 sigma caret 2 right sigma caret 2 caret 1 plus frac nu underscore 0 2 and propto left frac 1 sigma caret 2 right caret n 2 frac 1 sigma caret 2 caret 1 plus frac nu underscore 0 2 exp left frac s 2 sigma caret 2 plus frac nu underscore 0 sigma underscore 0 caret 2 2 sigma caret 2 right and equals frac 1 sigma caret 2 caret 1 plus frac nu underscore 0 plus n 2 exp left frac nu underscore 0 sigma underscore 0 caret 2 plus s 2 sigma caret 2 right end aligned. The above is also a scaled inverse chi-squared distribution where nu 0 equals nu 0 plus n nu 0 sigma o2 equals nu 0 sigma o2 plus I equals 1 n xi minus mu 2. Display style begin aligned nu underscore 0 and equals nu underscore 0 plus n nu underscore 0 sigma underscore 0 caret 2 and equals nu underscore 0 sigma underscore 0 caret 2 plus sum underscore I equals 1 caret n x underscore I mu caret 2 end aligned or equivalently nu 0 equals nu 0 plus n sigma O2 equals nu 0 sigma O2 plus I equals 1 n xi minus mu 2 nu 0 plus n display style begin aligned nu underscore 0 and equals nu underscore 0 plus n sigma underscore 0 caret 2 and equals frac nu underscore 0 sigma underscore 0 caret 2 plus sum underscore I equals 1 caret n x underscore I mu caret 2 nu underscore 0 plus n end aligned reparameterized normalizing in terms of an inverse gamma distribution, the result is alpha equals alpha plus n2 beta equals beta plus I equals 1 n xi minus mu 2 display style begin aligned alpha and equals alpha plus frac n2 beta and equals beta plus frac sum underscore I equals 1 caret n x underscore I mu caret 2 end aligned. Topic with unknown mean and unknown variance. For a set of d, normally distributed data points x of size n where each individual point x follows x n mu sigma 2 display style x sim math call n mu sigma caret 2 with unknown mean mu and unknown variance sigma 2, a combined multivariate conjugate prior is placed over the mean and variance, consisting of a normal inverse gamma distribution. Logically, this originates as follows. From the analysis of the case with unknown mean but known variance, we see that the update equations involve sufficient statistics computed from the data consisting of the mean of the data points and the total variance of the data points, computed in turn from the known variance divided by the number of data points. From the analysis of the case with unknown variance but known mean, we see that the update equations involve sufficient statistics over the data consisting of the number of data points and sum of squared deviations. Keep in mind that the posterior update values serve as the prior distribution when further data is handled. Thus, we should logically think of our priors in terms of the sufficient statistics just described, with the same semantics kept in mind as much as possible. To handle the case where both mean and variance are unknown, we could place independent priors over the mean and variance, with fixed estimates of the average mean, total variance, number of data points used to compute the variance prior, and sum of squared deviations. Note however that in reality, the total variance of the mean depends on the unknown variance, and the sum of squared deviations that goes into the variance prior appears to depend on the unknown mean. In practice, the latter dependence is relatively unimportant, shifting the actual mean shifts the generated points by an equal amount, and on average the squared deviations will remain the same. This is not the case, however, with the total variance of the mean. As the unknown variance increases, the total variance of the mean will increase proportionately, and we would like to capture this dependence. This suggests that we create a conditional prior of the mean on the unknown variance, with a hyperparameter specifying the mean of the pseudo-observations associated with the prior, and another parameter specifying the number of pseudo-observations. This number serves as a scaling parameter on the variance, making it possible to control the overall variance of the mean relative to the actual variance parameter. The prior for the variance also has two hyperparameters, one specifying the sum of squared deviations of the pseudo-observations associated with the prior, and another specifying once again the number of pseudo-observations. Note that each of the priors has a hyperparameter specifying the number of pseudo-observations, and in each case this controls the relative variance of that prior. These are given as two separate hyperparameters so that the variance aka the confidence of the two priors can be controlled separately. This leads immediately to the normal inverse gamma distribution, which is the product of the two distributions just defined, with conjugate priors used, an inverse gamma distribution over the variance, and a normal distribution over the mean, conditional on the variance, and with the same four parameters just defined. The priors are normally defined as follows: p mu sigma 2 mu 0 n 0 n mu 0 sigma 2 n 0 p sigma 2 nu 0 sigma 0 2 I chi 2 nu 0 sigma O2 equals IG nu 0 halves nu 0 sigma 0 and 2 halves display style begin aligned p mu mid sigma caret 2 mu underscore 0 n underscore 0 and sim math call n mu underscore 0 sigma caret 2 n underscore 0 p sigma caret 2 nu underscore 0 sigma underscore 0 caret 2 and sim I chi caret 2 nu underscore 0 sigma underscore 0 caret 2 equals IG nu underscore 0 2 nu underscore 0 sigma underscore 0 caret 2 2 end aligned. The update equations can be derived and look as follows: x equals 1 n I equals 1 n x I mu 0 equals n 0 mu 0 plus n x n 0 plus n n 0 equals n 0 plus n nu 0 equals nu 0 plus n nu 0 sigma 0 2 equals nu 0 sigma 0 2 plus I equals 1 n x I minus x 2 plus n 0 n n 0 plus n mu 0 minus x 2 display style begin aligned bar x and equals frac 1 n sum underscore I equals 1 caret n x underscore I mu underscore 0 and equals frac n underscore 0 mu underscore 0 plus n bar x n underscore 0 plus n n underscore 0 and equals n underscore 0 plus n nu underscore 0 and equals nu underscore 0 plus n nu underscore 0 sigma underscore 0 caret 2 and equals nu underscore 0 sigma underscore 0 caret 2 plus sum underscore I equals 1 caret n x underscore I bar x caret 2 plus frac n underscore 0 n n underscore 0 plus n mu underscore 0 bar x caret 2 end aligned. The respective numbers of pseudo-observations add the number of actual observations to them. The new mean hyperparameter is once again a weighted average, this time weighted by the relative numbers of observations. Finally, the update for nu 0 sigma O2 display style nu underscore 0 sigma underscore 0 caret 2 is similar to the case with known mean, but in this case the sum of squared deviations is taken with respect to the observed data mean rather than the true mean, and as a result a new interaction term needs to be added to take care of the additional error source stemming from the deviation between prior and data mean. Occurrence and applications. The occurrence of normal distribution in practical problems can be loosely classified into four categories: exactly normal distributions, approximately normal laws, for example when such approximation is justified by the central limit theorem, and distributions modeled as normal, the normal distribution being the distribution with maximum entropy for a given mean and variance. Regression problems, the normal distribution being found after systematic effects have been modeled sufficiently well. Exact normality. Certain quantities in physics are distributed normally, as was first demonstrated by James Clerk Maxwell. Examples of such quantities are probability density function of a ground state in a quantum harmonic oscillator, the position of a particle that experiences diffusion. If initially the particle is located at a specific point, that is its probability distribution is the Dirac delta function, then after time t its location is described by a normal distribution with variance t, which satisfies the diffusion equation t f x t equals 1 2 2 x 2 f x t. Display style frac partial t f x t equals frac 1 2 frac partial caret 2 partial x caret 2 f x t. If the initial location is given by a certain density function g x display style g x, then the density at time t is the convolution of g and the normal PDF. Topic: Approximate normality. Approximately normal distributions occur in many situations, as explained by the central limit theorem. When the outcome is produced by many small effects acting additively and independently, its distribution will be close to normal. The normal approximation will not be valid if the effects act multiplicatively instead of additively, or if there is a single external influence that has a considerably larger magnitude than the rest of the effects. In counting problems, where the central limit theorem includes a discrete to continuum approximation and where infinitely divisible and decomposable distributions are involved, such as binomial random variables, associated with binary response variables, Poisson random variables, associated with rare events, thermal radiation has a Bose–Einstein distribution on very short time scales, and a normal distribution on longer timescales due to the central limit theorem. Assumed normality. I can only recognize the occurrence of the normal curve, the Laplacian curve of errors, as a very abnormal phenomenon. It is roughly approximated to in certain distributions. For this reason, and on account for its beautiful simplicity, we may, perhaps, use it as a first approximation, particularly in theoretical investigations. There are statistical methods to empirically test that assumption, see the above normality tests section. In biology, the logarithm of various variables tend to have a normal distribution, that is, they tend to have a log-normal distribution after separation on male-female subpopulations, with examples including measures of size of living tissue, length, height, skin area, weight. The length of inert appendages, hair, claws, nails, teeth of biological specimens, in the direction of growth. Presumably the thickness of tree bark also falls under this category. Certain physiological measurements, such as blood pressure of adult humans. In finance, in particular the Black-Scholes model, changes in the logarithm of exchange rates, price indices, and stock market indices are assumed normal. These variables behave like compound interest, not like simple interest, and so are multiplicative. Some mathematicians such as Benoit Mandelbrot have argued that log-Levy distributions, which possesses heavy tails, would be a more appropriate model, in particular for the analysis for stock market crashes. The use of the assumption of normal distribution occurring in financial models has also been criticized by Nassim Nicholas Taleb in his works. Measurement errors in physical experiments are often modeled by a normal distribution. This use of a normal distribution does not imply that one is assuming the measurement errors are normally distributed, rather using the normal distribution produces the most conservative predictions possible given only knowledge about the mean and variance of the errors. In standardized testing, results can be made to have a normal distribution by either selecting the number and difficulty of questions as in the IQ test or transforming the raw test scores into output scores by fitting them to the normal distribution. For example, the SAT's traditional range of 200 to 800 is based on a normal distribution with a mean of 500 and a standard deviation of 100. Many scores are derived from the normal distribution, including percentile ranks, percentiles, or quantiles, normal curve equivalents, stanines, z-scores, and t-scores. Additionally, some behavioral statistical procedures assume that scores are normally distributed, for example, t-tests and ANOVAs. Bell curve grading assigns relative grades based on a normal distribution of scores. In hydrology, the distribution of long-duration river discharge or rainfall, e.g. monthly and yearly totals, is often thought to be practically normal according to the central limit theorem. The blue picture, made with Cumfrec, illustrates an example of fitting the normal distribution to ranked October rainfalls showing the 90% confidence belt based on the binomial distribution. The rainfall data are represented by plotting positions as part of the cumulative frequency analysis. Produced normality. In regression analysis, lack of normality in residuals simply indicates that the model postulated is inadequate in accounting for the tendency in the data and needs to be augmented. In other words, normality in residuals can always be achieved given a properly constructed model. Topic: Generating values from normal distribution. In computer simulations, especially in applications of the Monte Carlo method, it is often desirable to generate values that are normally distributed. The algorithms listed below all generate the standard normal deviates, since an mu, sigma 2 can be generated as x equals mu plus sigma z, where z is standard normal. All these algorithms rely on the availability of a random number generator U capable of producing uniform random variates. The most straightforward method is based on the probability integral transform property. If U is distributed uniformly on 0, 1, then phi-1 U will have the standard normal distribution. The drawback of this method is that it relies on calculation of the probit function phi-1, which cannot be done analytically. Some approximate methods are described in Hart 1968 and in the ERF article. Wichura gives a fast algorithm for computing this function to 16 decimal places, which is used by R to compute random variates of the normal distribution. An easy-to-program approximate approach, that relies on the central limit theorem, is as follows: generate 12 uniform U 0, 1 deviates, add them all up, and subtract 6. The resulting random variable will have approximately standard normal distribution. In truth, the distribution will be Irwin-Hall, which is a 12-section 11th-order polynomial approximation to the normal distribution. This random deviate will have a limited range of -6, 6. The Box-Muller method uses two independent random numbers u and v distributed uniformly on 0, 1. Then the two random variables x and y. X equals -2 lane u cos 2 pi v y equals -2 lane u sin 2 pi v. Display style x equals sqrt -2 lane u cos 2 pi v q quad y equals sqrt -2 lane u sin 2 pi v. Will both have the standard normal distribution and will be independent. This formulation arises because for a bivariate normal random vector x, y, the squared norm x2 plus y2 will have the chi-squared distribution with 2 degrees of freedom, which is an easily generated exponential random variable corresponding to the quantity -2 lane u in these equations, and the angle is distributed uniformly around the circle, chosen by the random variable v. The Marsaglia-Polar method is a modification of the Box-Muller method which does not require computation of the sine and cosine functions. In this method, u and v are drawn from the uniform -1, 1 distribution, and then s equals u2 plus v2 is computed. If s is greater or equal to 1, then the method starts over, otherwise the two quantities x equals u minus 2 lane s y equals v minus 2 lane s display style x equals u sqrt frac -2 lane s q quad y equals v sqrt frac -2 lane s are returned. Again, x and y are independent, standard normal random variables. The ratio method is a rejection method. The algorithm proceeds as follows. Generate two independent uniform deviates u and v. Compute x equals square root 8 e v minus 0.5 u. Optional, if x2 5 minus 4 e 1/4 u, then accept x and terminate algorithm. Optional, if x2 4 e minus 1.35 u plus 1.4, then reject x and start over from step 1. If x2 minus 4 ln u, then accept x, otherwise start over the algorithm. The two optional steps allow the evaluation of the logarithm in the last step to be avoided in most cases. These steps can be greatly improved so that the logarithm is rarely evaluated. The ziggurat algorithm is faster than the Box-Muller transform and still exact. In about 97% of all cases it uses only two random numbers, one random integer and one random uniform, one multiplication and an if test. Only in 3% of the cases, where the combination of those two falls outside the core of the ziggurat, a kind of rejection sampling using logarithms, do exponentials and more uniform random numbers have to be employed. Integer arithmetic can be used to sample from the standard normal distribution. This method is exact in the sense that it satisfies the conditions of ideal approximation, i.e., it is equivalent to sampling a real number from the standard normal distribution and rounding this to the nearest representable floating point number. There is also some investigation into the connection between the fast Hadamard transform and the normal distribution, since the transform employs just addition and subtraction, and by the central limit theorem random numbers from almost any distribution will be transformed into the normal distribution. In this regard, a series of Hadamard transforms can be combined with random permutations to turn arbitrary data sets into a normally distributed data. Numerical approximations for the normal CDF. The standard normal CDF is widely used in scientific and statistical computing. The values phi x may be approximated very accurately by a variety of methods, such as numerical integration, Taylor series, asymptotic series, and continued fractions. Different approximations are used depending on the desired level of accuracy. Shor 1982 introduced simple approximations that may be incorporated in stochastic optimization models of engineering and operations research, like reliability engineering and inventory analysis. Denoting p equals phi z, the simplest approximation for the quantile function is z equals phi minus 1, p equals 5.5556 1 minus pp 0.1186 p 1/2. Display style z equals phi caret minus 1, p equals 5.5556 left 1 left frac 1 p right caret 0.1186 right q quad p geq 1/2. This approximation delivers for z a maximum absolute error of 0.026 for 0.5 p 0.9999, corresponding to 0 z 3.719. For p z equals minus 0. 4115 1 minus p plus log 1 minus p minus 1 p 1 2. Display style z equals minus 0.4115 left frac 1 p plus log left frac 1 p right minus 1 right q quad p geq 1/2. The latter had served to derive a simple approximation for the loss integral of the normal distribution, defined by L z equals z infinity u minus z phi u d u equals z infinity 1 minus phi u d u L z approximately equals 0. 4115 p1 minus p minus z p 1/2 0.4115 1 minus pp p 1/2, or equivalently L z approximately equals 0. 4115 1 minus log p1 minus p 1/2 0.4115 1 minus pp p 1/2. Display style begin aligned L z and equals int underscore z caret inft u z var phi u do equals int underscore z caret inft 1 phi u do 5 pt L z and approximately begin cases 0.4115 left dfrac p 1 p right z and p. This approximation is particularly accurate for the right far tail maximum error of 10-3 for z 1.4. Highly accurate approximations for the CDF, based on response modeling methodology (RMM), Shore, 2011, 2012, are shown in Shore 2005. Some more approximations can be found at error function #approximation with elementary functions. In particular, small relative error on the whole domain for the CDF phi _phi and the quantile function phi -1 phi -1 as well, is achieved via an explicitly invertible formula by Sergei Winitsky in 2008. History. Development. Some authors attribute the credit for the discovery of the normal distribution to de Moivre, who in 1738 published in the second edition of his The Doctrine of Chances, the study of the coefficients in the binomial expansion of A plus B n. De Moivre proved that the middle term in this expansion has the approximate magnitude of 2 pi n display style 2 sqrt 2 pi n, and that if m or 1/2 n be a quantity infinitely great, then the logarithm of the ratio, which a term distant from the middle by the interval has to the middle term, is minus 2 n display style frac 2 l n. Although this theorem can be interpreted as the first obscure expression for the normal probability law, Stigler points out that de Moivre himself did not interpret his results as anything more than the approximate rule for the binomial coefficients, and in particular de Moivre lacked the concept of the probability density function. In 1809 Gauss published his monograph, Theoria motus corporum coelestium in sectionibus conicis solum ambientium, where among other things he introduces several important statistical concepts, such as the method of least squares, the method of maximum likelihood, and the normal distribution. Gauss used m to denote the measurements of some unknown quantity v, and sought the most probable estimator of that quantity, the one that maximizes the probability phi m-v phi m-v phi m-v of obtaining the observed experimental results. In his notation, Ph.D. is the probability law of the measurement errors of magnitude delta. Not knowing what the function phi is, Gauss requires that his method should reduce to the well-known answer, the arithmetic mean of the measured values. Starting from these principles, Gauss demonstrates that the only law that rationalizes the choice of arithmetic mean as an estimator of the location parameter, is the normal law of errors. Phi delta equals h square root pi e minus h delta display style varphi mathet delta equals frac h surd pi e caret mathrm h delta, where h is the measure of the precision of the observations. Using this normal law as a generic model for errors in the experiments, Gauss formulates what is now known as the nonlinear weighted least squares (NWLS) method. Although Gauss was the first to suggest the normal distribution law, Laplace made significant contributions. It was Laplace who first posed the problem of aggregating several observations in 1774, although his own solution led to the Laplacian distribution. It was Laplace who first calculated the value of the integral e minus t 2 dt equals square root pi in 1782, providing the normalization constant for the normal distribution. Finally, it was Laplace who in 1810 proved and presented to the Academy the fundamental central limit theorem, which emphasized the theoretical importance of the normal distribution. It is of interest to note that in 1809 an American mathematician Adrain published two derivations of the normal probability law, simultaneously and independently from Gauss. His works remained largely unnoticed by the scientific community, until in 1871 they were «rediscovered» by Abbey. In the middle of the 19th century, Maxwell demonstrated that the normal distribution is not just a convenient mathematical tool, but may also occur in natural phenomena. The number of particles whose velocity, resolved in a certain direction, lies between x and x plus dx is n 1 alpha pi e minus x 2 alpha 2 d x. Display style operator name n frac 1 alpha sqrt pi e caret frac x caret 2 alpha caret 2 dx. Topic: Naming. Since its introduction, the normal distribution has been known by many different names: the law of error, the law of facility of errors, Laplace's second law, Gaussian law, etc. Gauss himself apparently coined the term with reference to the normal equations involved in its applications, with normal having its technical meaning of orthogonal rather than usual. However, by the end of the 19th century some authors had started using the name normal distribution, where the word «normal» was used as an adjective, the term now being seen as a reflection of the fact that this distribution was seen as typical, common, and thus «normal». Peirce, one of those authors, once defined «normal» thus: The normal is not the average or any other kind of mean of what actually occurs, but of what would, in the long run, occur under certain circumstances. Around the turn of the 20th century, Pearson popularized the term normal as a designation for this distribution. Many years ago I called the Laplace-Gaussian curve the normal curve, which name, while it avoids an international question of priority, has the disadvantage of leading people to believe that all other distributions of frequency are in one sense or another abnormal. Also, it was Pearson who first wrote the distribution in terms of the standard deviation sigma as in modern notation. Soon after this, in year 1915, Fisher added the location parameter to the formula for normal distribution, expressing it in the way it is written nowadays: d f equals 1 2 sigma 2 pi e minus x minus m 2 2 sigma 2 d x. Display style df equals frac 1 sqrt 2 sigma caret 2 pi e caret xm caret 2 2 sigma caret 2 dx. The term standard normal, which denotes the normal distribution with zero mean and unit variance, came into general use around the 1950s, appearing in the popular textbooks by P. G. Hole 1947, Introduction to Mathematical Statistics, and A. M. Mood 1950, Introduction to the Theory of Statistics. When the name is used, the Gaussian distribution was named after Carl Friedrich Gauss, who introduced the distribution in 1809 as a way of rationalizing the method of least squares as outlined above. Among English speakers, both «normal distribution» and «Gaussian distribution» are in common use, with different terms preferred by different communities. See also: Wrapped normal distribution, the normal distribution applied to a circular domain; Bates distribution, similar to the Irwin-Hall distribution, but rescaled back into the 0 to 1 range; Behrens-Fisher problem, the long-standing problem of testing whether two normal samples with different variances have same means; Bhattacharya distance, method used to separate mixtures of normal distributions; Erdős-Kac theorem on the occurrence of the normal distribution in number theory; Gaussian blur convolution, which uses the normal distribution as a kernel; normally distributed and uncorrelated does not imply independent; standard normal table; sub-Gaussian distribution; sum of normally distributed random variables; Tweedy distribution. The normal distribution is a member of the family of Tweedy exponential dispersion models; Z-test, using the normal distribution; Stein's lemma. Notes